Yeah. So if you see, uh, so this is a evaluation of logic complexity in ICs. So first, there is a mid-scale integration. So mid-scale integration means they introduced around 1967. So in medium scale integration, that logic, whatever the logic blocks per chip is 22 200 only. Okay, 22 200. And next, if you see, large scale integration. So large scale integration introduced around 1972. So logic block per chip is 200 to 2000. And VLSI is nothing but very large scale integration. It is introduced around 1978, and logic block per chip is 2000 to 20,000. So mostly means now, like we call as VLSI, and we are working under this VLSI. We do not went to ULSI. ULSI is nothing but ultra large scale integration. This is introduced in 1989, and the logic blocks is more than 20,000. Okay, so this is the evolution of complexity in ICs. And if you see the evolution size in the integrated services, so as per Moore's law, the transistor count in the transistor count in IC will be double for every 2 years, no, 18 months or 2 years. So that means here, if you see the minimum feature size, and this is technology. So technology, this is in terms of micrometer, and this is the year. So in 1975, we are in 4 micrometer technology, and in 2000, so it came into gradually, it is decreasing exponentially, it is decreasing, and we came up to zero point 0.1 micrometer technology. So the technology is nothing but the length between source and drain, and now we are working under 3 nanometer or 2 nanometer technology. Okay, so this is evolution of size in integrated services. And prominent information technology services, suppose like in 1975 to mid 80s, mainframe computers came, and 1985 to 1990 personal computers came, and 1995 to 2000 computer networks came. Okay, and between 1980s there is a consumer electronics. Consumer electronics means whatever the electronics we are using in the household, that is consumer electronics. And portable computers in 1990, portable computers came, laptops. Okay, so now we are using laptops. No, in 1990s this portable computers came. And data communication, so 1980s you got data communication, and we have multimedia related, like gaming part, it's introduced in 1990. And 1985, wireless or cellular data communication came. So that is related to the communication. Basically they started with GPRS, and next 1G, 2G, 3G, 4G. Now we are in 2020, we means they introduced 5G technology, and we are in the development of 6G technology also. Okay, and next in 1990s, speech processing came. And in 1990s, so video on demand, so basically some video related thing, that is video on demand on the 1990s you got. So these are the prominent information technology services. Okay, hope you understood. Am I audible now? Give response. Hello. Yes.
Yes, sir.
Okay, yeah. So these are the prominent information technology services. And next, so features of integrated circuit, if we see, that should be less area or volume, and less power consumption, and less testing requirement at system level, and higher reliability, mainly due to improved on chip interconnects, higher speed, and mainly due to reduced interconnect length and significant cost saving. These are the, so if you take any integrated circuits, these that IC should satisfy all these parameters. Okay, all these features it should satisfy. Okay, so if you see methodologies. Okay, so what are the methodologies? Design time, performance analysis versus design time, and technology window. Okay, so design time means what? So design time means IC design depends on these parameters: design complexity, performance level, and acceptable cost. Okay, so like so suppose here design complexity, performance level, and acceptable cost means here if you see. So this is the performance analysis versus design time. Suppose there are two types of designs are there. That is nothing but full custom and semi-custom design. Okay. So full custom and semi-custom means where here you see. Okay. Full custom. So before this, I want to explain about full custom and semi-custom. Full custom is nothing but we'll start the design from the scratch. That means complete design and layout, geometry, orientation, and placement of the transistor is done by the designers. Okay. And here semi-custom means some commonly used designs, layout, geometry, and placement of transistor is inferred with given demand. So that means already some standard library cells are available. So that is already designed and tested. So they will make this, and they will make as a semi-custom design. Okay. So that means here a full custom design means they will start from the scratch, and here semi-custom design means already whatever the standard cells are there, like standard cells are available in terms of flip-flops, gates, counters, like that. So they will, so already that design is tested, and with some design rules, with the technology they will take and they will implement in their design. Okay. Here full custom means entire design they will made without any library. Here design is completed, so they will design completely on multiple libraries. Okay, they will use multiple libraries. Okay. So development time for design before maturity is more, and development time design before maturity is less. Okay, here development time is less. Okay, why? Because already pre-designed standard cells they are taking out and they are implementing in this design. Okay, I will tell you with example, you can understand very well. Here development, so they will here development time is very very much. It will take I think it will take suppose semi-custom design, it will take 6 months of time. Full custom design, it will take 1 year of time. Okay, development time is more in the full custom design. Okay, it has more it has more opportunities for performance improvement. Performance improvements have more opportunities in full custom design, and performance in improvements are not that much. Those are less in semi-custom design. Okay, and full custom design, it is less depends on existing technology, and semi-custom design completely depends on whatever the technology we have. Okay, and full custom design, so it is high cost, and semi-custom design, it is low cost. Suppose if you see this one, so that means this one, so this is nothing but what? This is nothing but semi-custom design. So semi-custom design start from, so it will start from here. Okay, so it will start from, 1 second, I will draw. So semi-custom, it will start from this state. It will start from this state, and full custom, it will start from the lowest level. Okay. After that, so this is nothing but design time. So this is the shortest design time. Okay. Until maturity, it is having the shortest design time. Here until maturity, it is having the longest design time. Okay, it will longest. So let us take full custom design, it will take 1 year of time. Semi-custom design, it will take 6 months. It will take 6 months. After that, it becomes constant. Okay, so let us take example like full custom design. Like full custom design means like you have iPhones. Okay, Apple iPhones, and you have Samsung mobile phone. I am taking the example of these phones. Okay, so that means here if you take the iPhone, so iPhone will start from iPhone 6, 7, 8, 9, 10. Okay, so every model, it will take 1 year of time. So that means 1 year of time. Samsung also, here you have like Note 6, Note 7, Note 8, Note 9. So that means these they will provide, means they will build these phones from the full custom design. From the scratch, they will made their own chips, and they are not depending on the library. Okay, that's why cost is more for iPhones and Samsung mobiles. Suppose if you see the, so that comes under the full custom design. Okay, full custom. Semi-custom design means, suppose if you take Vivo, okay, Vivo or Oppo phones or MI phones. Okay, MI phones. These are nothing but this is having like means all features are available. So compared to this is one third of low cost. No? One third of low cost. So that means like it will be around with all features it will be 25,000. But same features if you want in iPhone and iPhone or Samsung, it will be around like I think 1 lakh 80,000 it will be available. Why? Because it is based on the full custom design. Whereas these people what they will do, they will take the whatever the standard cells are available. Suppose MI phone is there. So MI phone what they will do? So they will take the processor from Qualcomm. Okay, Qualcomm Snapdragon processor. Okay, so different modules they will take already available modules are there. They will take and they will make as a system. Okay, so this is about the full custom and semi-custom design. Hope you understood the difference between the what is full custom and semi-custom design. Give response. Hello. Hello. Yeah. Do you understood? Give response. Anyone?
Yes, sir.
Okay. So if you understood means I will move forward. Okay. So technology window means what? Technology window means so circuit performance with what technology window. Suppose any product is there. So any product. So here this is design and this is production. Okay. So here suppose one model is came. Okay. One model like if you take suppose iPhone 7 model, this model came after 1 year. So whatever the specifications are there, it should start from means it should be improved version of this design. Means suppose they release iPhone 8, so it should start from the improved version. Okay, so it should not degrade like this. Okay, it should start from the improved version. Okay, so this is first technology, whereas it is implemented in iPhone 7. In iPhone 8 it should start from whatever the improved features in this iPhone 7. Okay, so this is the technology window. Okay, and semi-custom and full custom. So that means whatever this ASICs, so ASICs are nothing but so ASIC design is there, no? So from the scratch they will design. So ASIC design, application specific integrated circuits. This is full custom design. Okay, and next performance analysis I told you design. Okay, performance analysis. Semi-custom. So what are the semi-custom? Basic semi-custom design and classification of semi-custom design and working of different semi-custom design. Okay, so semi-custom design I told you. So what is the semi-custom design? So here by using semi-custom design they will what they will do, they will reduce the time to market. So they will reduce the time to market. As I told you the example, no, suppose iPhone is there. So iPhone it will take to make the product and to release into the market, it will take 1 year of time. So if you take like suppose Oppo, Vivo and MI phones are there, that phones within the 6 months they will release 2 or 3 models. Okay, so what is the difference means here they are using semi-custom design. Okay, these whatever the these phones are there, they will follow the semi-custom design. So that means to reduce the time to market they use this semi-custom design. Okay, and also to reduce the cost of designing product. Okay, so that means if they come with the scratch it will take so much of cost. Okay, so whatever the predefined IPs are available, just they will take from this whoever the designing those IPs, like suppose like processor is there, they will purchase from like Qualcomm Snapdragon processor is there, no, Qualcomm company, or DSP processors are there, so from DSP company, so for audio related thing they want DSP processor, they will purchase from DSP related companies. They will provide that which are designed and pre-tested. Okay, but performance is lesser if you compare with full custom design. Performance of semi-custom design is lower than the full custom design. Okay, full custom design. In semi-custom design we use really, so I told you, no, So we use readily available blocks, design and library and modules. Okay, so whatever the readily available are there, so that we are taking and we are designing in our module. Okay, in our system. Okay, so this is semi-custom design. And so if you see the classification of semi-custom design, there are like three types are there: standard cell, gate array and programmable logic devices. Okay, programmable devices. So standard cells are nothing but here if you see the standard cells, so we use the standard cells. So standard cells means, I told you, no, so standard cells means basically those are available in like inverters. Okay, so they have some hundreds of cells are there. So inverters, NAND gates, NOR gates, complex AOI, that means AND or invert logic or and invert logic gates, D latches, flip flops, okay, counters. Okay, so these whatever the digital circuits are there, digital circuits are readily available as a standard cell. In which design? That is standard cell. Okay, so those we are using in the semi-custom design. So in the library there are the gates with the different driving capabilities. For example, suppose gates are there, AND gate and NOR gate are there. So they have some specific driving capabilities like standard size and double size, quadruple size. Okay, so we need to use this whatever the AND gates or gates depending on our requirement. Okay, depending on our requirement you can use. Okay, so what the designer will do? Designer send the schematics. I want this type of schematics to the fabricator. So based on the requirement of the designer, fabricator will prepare the mask. If the cell is from library. Okay, so larger the library, larger the cost. Okay, so standard cell guarantees that it will work based on its functionality. Suppose gates are there, what is this functionality? NAND gate is there, what is this functionality? You know, NOR gate is there, what is this D latch, flip flop. Okay, you know the functionality already we see in the digital. Okay, counter means it will count the number of clock pulses. Okay, so what are the advantages of standard cell? Means flexible design. It is flexible design. So flexible, there is a flexibility to design. We can work with both analog and digital functions, and sophisticated system. So whatever the complex systems are there, complex systems also we can build easily. Why? Because we already have the standard cells, no, predefined cells are available. So whatever the complex SoC are there, system on chip are there, we can design easily. Okay, disadvantage, mask cost is more. Okay, so mask cost is more. Okay, this is about the standard cell. Hope you understood. And gate array is nothing but prefabricated circuit with no particular function. Okay, that is fabricated but without any connections. Gate array is nothing but basically you have FPGA. Okay, and next CPLD. This comes under the gate array. Which transistors and other devices are placed at a regular predefined position. Okay, so this we can use for gate array, we can use for R&D purpose only. So we can see if I want to design a half adder or full adder, if I want to design a counter. Okay, so we can use this gate array. This is one mask for metallization need to be created. So reduce what are the advantages? Reduce the mask cost and less time to market. Okay, so disadvantage is size is fixed. We can't decrease the size, and number of transistors are fixed. Metal height is fixed, 2 metal layer, and low efficiency and suitable for low production value. Okay, and PLDs we already discussed. So PLDs are nothing but there are varieties of ICs available. SPLD, that is nothing but simple programmable logic device. CPLD, complex programmable logic device, and field programmable gate arrays. Okay, so CPLD and this one. Okay, basically what is this means what is the difference between CPLD and FPGA? Means this is having like a less clock period, like 10 kilohertz it have. Okay, it consists of more clock period, like in terms of 1 gigahertz it have. Okay, and for storing this it will use for storing the program it will use PROM. Okay, for this one it will store SRAM. Okay, you know that we already seen PROM is nothing but what? Non-volatile. Whatever the program you are storing in the CPLD, so that will be permanently stored. Okay, see here what happens, this is nothing but SRAM is nothing but volatile. So volatile means once the power is switched off, so whatever the programming part in the FPGA, that will erase. Okay, again you need to program. Okay, so that is the difference between complex CPLD and FPGA. Okay, so there is hierarchy, regularity, modularity and locality. Hierarchy is nothing but like suppose complex system is there. So complex system is subdivided into what? Modules, and modules are subdivided into like gates. Gates are subdivided into divided into circuits. Okay, so that means whatever the complex design if you take, okay, so that is into various modules and sub modules. Okay, so we need to divide. Okay, we need to divide this complexity of sub modules into understandable level of detail. So they need to come with low level. Okay, so like means if you see hierarchy, first system, and next let us take system means what? SOC, and here processor. After that processor you have we have modules. Modules are made with what? Gates, and gates are made with like CMOS, and CMOS is made with the transistor, MOSFET. So this is nothing but what? Hierarchy. So that means this we call as top down approach, and from here to here this is nothing but bottom up approach. So like this we can do this modularity. Okay, this is hierarchy. Okay, so we need to understand from the like system, we need to divide into different modules and gates and CMOS and MOSFET. Okay, regularity is nothing but so whoever the designers are there, divide the hierarchy into set of similar building blocks. Okay, they will design with set of similar building blocks like transistor level, gate level, micro level and macro level. Okay, so macro level means in terms of it consists of some macros, different types of like processor, SRAM, RASRAM, I2C, SPI, and UART protocol, UART peripherals. Okay, this is macro level. Okay, and next micro level and gate level and transistor level. This is like regularity. Okay, modularity means so this is the functional block has well defined functions, interfaces, so that they can be tested separately. Okay, so blocks can be combined easily to end of the design. Okay, this is modularity. Locality means so that whatever the interior modules are there that are not visible to any exterior interface. Okay, that is locality. Okay, so when you are designing that, you need to consider these things. That means hierarchy, regularity, modularity and locality. Okay, so modularity and locality. And package technology means here through whole package, surface mount and contactless. So through whole package means ICs how are there? I think you already studied. There are like SIP, single inline package, DIP, dual inline package and FPGA, pin grid array. So SIP means what? Only single side the pins are available. That is nothing but so IC package having the single low leads. Those are nothing but single line packages. So okay, it has less number of leads. Most in dual line package in your engineering college you are using these ICs. That means two sides the IC pins are available. Okay, so having two rows in the leads. Okay, DIP is almost used in educational institutions. In your lab you already seen the digital lab or like that, you are using the IC in two sides. Here two sides are there. IC will be two sides. Okay, and next here package grid array means there is a grid arrangement. Suppose if you take the processor, inside the processor, so like this these leads are there. Okay, here leads are there, here leads are there. Okay, inside the processor, here leads are below this processor, these leads are there, these leads are there. So this is nothing but we call as a package grid array. Okay, so they offer more number of leads, maximum 400 pins. You can see processor IC, So that is nothing but it is based on the package grid array. Okay, it's better than DIP in terms of thermal conductivity and power dissipation characteristics. Okay, surface mount means like one IC will be there. So it will be like surface mount means it doesn't consist of leads. It will be like surface mounted like this. It will be there. Okay, like this surface mount. Okay, so unlike whole package, so that means if whole packages are there means within the PCB you can insert based on the design and you can solder. These consist of leads. These consist of leads on amount of in surface mount of package. Okay, so they are mounted directly on the surface of PCB. Okay, so they do not go through the holes or fit to the socket. Okay, so basically their mount package is bent. I told it will be bent. It will be bent, and there's some angle near to foot. Okay, so there are ball grid also. Ball grid means suppose one IC is there. This IC is there. So inside, in place of this leads, there are balls type like this is there. This is nothing but ball grid. This is nothing but, so it has a metal balls. It does not have the solder. By little pressure we can fix it to the PCB. So by using little pressure we can fix it. It has many terminals. Okay, it will be like 56 to 1312 terminals. It can be packaged from multiple sides. Okay, it can package from multiple sides. Okay, so this is surface mount package. Contactless means what? It does not have any physical contact. Okay, it does not have any leads. Okay, and it provide information wirelessly. How it is providing information means it is providing the information wirelessly. Okay, so this is contactless process. So you know the VLSI design flow. Basically in VLSI design flow you will follow the so first it will start from the specification. Okay, and so after that at end you should get whatever the requirement is there, that should satisfy. So design specification. Okay, design specification means what are the inputs and what are the outputs and what is the functionality of the circuit. That is comes under design specification. Architectural design means you are designing over the module level, CPU and RAM level. Okay, and module level. Okay, so that is nothing but architectural level. Okay, what are the peripherals, I2C, SPA. Module level design is nothing but architectural design. Gate level design means you are designing in terms of gates. Circuit level means in terms of circuits you need to design. First you need to design this one. After that HDL coding. So you can write the coding, hardware descriptive language, Verilog or VHDL. You can write the program in Verilog and VHDL. Whatever the program you are writing, you need to simulate. Means whether your functionality is correct or not, with the waveforms you need to simulate. Okay, you need to simulate. Okay, after that your circuit is correct or not, you need to use verification. Verification means what? Basically you are using system Verilog and UVM related methodologies to verify this circuit. If design is meet, it will go to the fabrication. If design is not meet, again it will go to the design HDL code. Okay, so this is the flow chart of VLSI design flow. So basically domains in VLSI, if you see, there are three domains are there: behavioral domain, structural domain and physical domain. Okay, so behavioral domain means it will shows the behavior of the circuit, structure of the circuit, and physical domain. Okay, so if you see the Y chart, VLSI Y chart, first it will start from where? So this is the first one, algorithm. It will start from the behavioral domain. So behavioral domain means you need to write the algorithm. You need to write the programming in that means HDL, hardware descriptive language. So you have algorithm, that means set of instructions, set of steps. Based on the steps you need to write the program. Okay, for program algorithm. Okay, after the structural domain you have a system. Structural domain, in the structural domain you have a system. Okay, and after system, in physical domain you have what? Floor planning. You have floor planning. Okay, so floor planning, chip floor plan. So you need to do some floor in physical domain. You need to do some chip floor plan. Floor planning is nothing but where the module should come, and that is you need to do some place means floor planning. Okay, next this one you need to, it will go to finite state machine, FSM. Okay, so how the physical layers are connected, and so that will comes under the finite state machine. Okay, and next it will come to the register. Okay, now a finite state machine is made up of register. Okay, after that module placement. Okay, it will come to the module placement, and after that module description. What is the description of that module? Okay, module description. And next, so next module description, and next they are representing in a, so we'll do some synthesis. So synthesis is nothing but we are converting whatever the program into gate level netlist. That is nothing but we are representing in terms of gates, that is logic gates. Okay, this is eighth. Okay, logic gates. And after that cell placement. Okay, where we need to place the cell, that is comes under the placement. Okay, and boolean equation. Okay, boolean equation. And next that is in terms of transistors, that is represented in terms of transistor. And next you need to go for fabrication, that is nothing but mask. Okay, so this is the Y chart. It will follow the in the VLSI design. Okay, so basically first, so there are mainly three are there. One is behavioral domain, and next is structural domain, and this next is physical domain. Okay, so algorithm and system, chip floor planning, finite state machine, register, and module placement, module description, module description, and logic gates, cell placement, boolean equation, transistor, and mask. Okay, so like this we will get, this is a Y chart for VLSI. Okay, importance of CAD tools. Why we are using CAD tools means, so these are the outlines, basic CAD tools in VLSI, IC design process, IC fabrication process, important features of CAD tools. So CAD tools means, as I told you, as per Moore's law, complexity of IC increases over the year. So that means whatever the ICs means number of transistors in an IC doubles. So he told that doubles for every 18 months. So till now Moore's law is satisfying. So that means what? Designing this VLSI circuit with millions of transistors in single IC is beyond human brain. So that means with 100 transistors, 10 to 100 transistors, we can make planning, or like we can verify that circuit. But millions of transistors are there. So it is difficult to verify that circuit or IC. Okay, that is beyond the human brain. So to design these circuits, we require computer. So that means to check the layout, circuit performance, and process. Okay, so this is used to design the so computers are used to aid the design and optimization process. We are using computer to aid the design. So there you got a CAD tools. CAD tools are nothing but what? Computer aided design. Computer aided design. For front end, you have some designers like front end Synopsys, VCS tools, Xilinx, Quartus Prime. Okay, these are for for synthesis also you have Synopsys tools like that. And for back end you have Cadence tools and Synopsys tools. Okay, so these are the some CAD tools which will guide. We need to give some guidelines to this tools, so that it will do the all the optimization and whatever the designing. Okay, so here whoever the VLSI designers are there, what they will do? Normally they will give a set of design rules based on the given technology. They will give that set of design rules for based on the given technology. Okay, so given technology they will give the some design rules for this CAD tools. Okay, so IC design process, if you see, design entry. After design entry, you need to do design verification and design rule check and simulation, and there is a pattern generation. After that, produce a mask. Okay, after producing a mask, each layer of mask processing and deposit and export it to the development edge. Packaging. After packaging, there is a testing. Okay, so this is the IC design process. So what are the features of VLSI CAD tools? Means there is a physical design. In physical design, You can do layout, editor, circuit schematic, like this you can do in the physical design. Physical verification means you need to check some, means you need to verify some rules. Those are nothing but design rule checks, circuit extraction, parasitic extraction, plot output, visual checking, okay, and behavioral verification, behavior of the circuit, okay, behavior of the chip, okay. So these are the features of VLSI. And next, if you see the comparison between FPGA and CPLDs, so parameter, FPGA and CPLD. So what is the full form? Full form of this FPGA is nothing but field programmable gate array, and this is nothing but complex programmable gate array. So architecture is based on, this is nothing but lookup tables, LUTs, okay. So LUT is nothing but lookup tables, okay. So this is based on logic function. Logic function means it have some combinational logic, and after that there are some flip-flops, okay, flip-flops like that, and one more mux will be there, okay. So like this, this function will be there. So blocks in the architecture around this is 1 lakh blocks will be there. Here only few blocks are available, okay. Architecture is tuning to, this is fine grain and this is coarse grain. So fine grain and coarse grain means, as I told you, so this is having the clock frequency of 1 gigahertz, means what, 10 power 9 cycles per second, 10 power 9 cycles per second, okay, it will process. Here you have only 10 kilohertz. 10 kilohertz means what, 10 power 4 cycles per second. So that is nothing but fine grain, and this is nothing but coarse grain, okay. And as I told you, FPGA it will use SRAM. SRAM is nothing but volatile. Volatile means what, once power is gone, whatever the program, that will be erased. Again you need to program in the FPGA. Whereas in a CPLD, this is EEPROM. EEPROM means it will be so permanently stored. This is non-volatile. This is volatile. So EEPROM means this is permanently stored. Okay. Complexity is high, so more number of blocks are there, no. Here complexity is less. Cost is high. Anyway, this cost is high, okay. This is less, okay. It will take some time to load the program. Instantly it will on, okay. Why? Because program will store, no. So instantly it will on. So volatility of program. So program once, so program lost once power is off. So program stays in CPLD. Why? Because we are using what, EEPROM. ROM we are using, okay. And ideal power consumption, weaker power consumption, complex to determine and easier to determine, okay. So this is about the comparison of FPGA and CPLD. So if you see, these are nothing but CPLDs which are having lookup tables. This is the logic block, and this is interconnect, and these are nothing but output connections, okay. So you have a lookup table, flip-flop, and mux. This is nothing but one configurable block, okay. So this is combinational block. This is combinational block, and this is a sequential block, and this is nothing but mux, okay. So this is nothing but configurable block. Okay. So this is about this. So this is about a clock distribution. There are setup time and hold time, like that it is there. And if you see, so what is the comparison between FPGA, CPLDs, programmable logic controllers, microprocessor, microcontroller, and DSP. So this is the full form. FPGA, you know, CPLD, you know, programmable logic control, microprocessor, microcontroller, digital signal processor, okay. This is the so this is the full form. And next, architecture, it is based on lookup table. This is based on logic blocks, and it has CPU, IO ports, and memory. And this is consist of CPU and IO ports, and basically it is basically von Neumann, and this is Harvard architecture, okay. Application, real-time application, okay. Coarse tuning application, industry application. PLCs are industry application. For high power and high temperature, we will use PLCs. Computer applications, consumer electronics, okay. We use for consumer electronics like cameras, automobiles, and household applications will use this consumer electronics, and real time applications like wherever the voice related or voice related applications are there, voice, image, image related operation, these type of applications will use DSPs. Okay, faster for real time, slow, and this is slow, and optimized for speed only, this is slow, and faster for real time. Immunity with noise, this is very good, moderate, highest, needs additional setup, low, good. Okay, task, this is not designed for multitasking, it is designed for only single tasking. Suppose if you want to design a counter, and if you put the whatever the program into this FPGA, that can be used as what, counter only. Okay, so it can't design for multitasking, only single task it will do. It is also single task, it is also single task. Microprocessor, it can do the multiple tasks. So your laptop is there, you are using multiple tasks, or in your mobile also processor is there, so you are doing multiple tasks in your mobile, no? So that is a processor, and this is not used designed for multiple tasks, this is used for specific task, specific application. Okay, this is also not designed, so this is used for image and voice related application. Turn on time, it is time, it takes time to on, it is less time, and it is also less time, it takes times to on, and this also takes time to in terms of microseconds. Okay, less time, it also less time, it will take nanoseconds. Okay, cost is expensive, cheap, expensive, this is also expensive. Microcontroller is cheap. Okay, this is expensive. Suppose 8051 microcontroller, if you take 8051 microcontroller or peripherals are available, this is available in with 100 rupees chip, one chip it is available. Okay, so one project is there, project one, if you are using microprocessor, it will cost around 1000 rupees, whole project cost. Same project, you are using microcontroller, it will cost around let us take 500. Which one will you prefer? This one only, no? Cost is also important. Okay, so this is about the VLSI, whole VLSI. One second.